I'll continue talking about braided fusion categories, and so let me explain the word braided in the name. Of course, it has to do with representation with braid groups. So I'll mention the Young-Baxter equation, braid groups that gave name to this theory. So the Young-Baxter equation is this thing. So let me write an equation, then I'll explain. So suppose you have three objects, x, y, and z, and then you can write ty tensor rs x z, and then it would be c y z identity x on one side. On the other, we would have identity x tensor c y z, and then cxz identity y, and cxy identity z. Sometimes you would see a picture that represents this equality, so it would look something like this. So the braiding is usually depicted like this by crossing of two strands. Okay, so this is braiding. Then this picture, the corresponding picture, will look like this. So this, and then that, and then that. So this picture involving a braid on three strands, and that should be the same as this, which really amounts to sliding, one braid past the crossing, right? One of the strands past the crossing. So here I've used notation a little bit. So here I omitted associativity constraint, which is like a common thing that people do, and there is a justification for that. Namely, there is a theorem of Maclaurin that says that every category is equivalent, every tensor category is equivalent to the one where associativity constraints are identity. So this is accomplished at the price of changing the number of objects in the category. Okay, so wow, this suggests, of course, this is the braid group relation. And so let's recall what a braid group is. So a braid group on n strands, Bn notation, on n strands has generators I, where sigma I, they correspond to elementary braids. So braids that look like this, where this is the ith and ith plus first positions. And they are subject to relations that braids that at least two indices apart commute, and braids that are next to each other, elementary braids that are next to each other, satisfy this relation. Now, if you look at the last relation, that's precisely the picture I draw here, right? Two adjacent braids satisfy this commutativity condition. So from this, we can deduce the following, that given an object V in C, where I C is a braided tensor category, there is a representation, let's call it, I don't know, rho of the braid group on the endomorphisms of the n tensor power of n, where the elementary braid sigma I would act as braiding on the ith and ith plus first positions, right? So this would be identity. Let me see if I get powers right, something like this. And then the braiding of V with itself. And then again, identity. How many times? I minus 1 times, right? So the sum should add to n. In other words, so the ith braid is like written here, and it's every strand, every end of direct strand correspond to identity of V. This corresponds to braiding. Okay, so this justifies the name braided tensor category. And of course, this is the source of all interesting applications of braided tensor categories to low-dimensional topology, invariance of nodes, and the manifolds. So we saw examples. Any questions so far, by the way?
Sorry, can we have a microphone, please? Who's got
the microphone? How do we read this bottom from top? Well, we need to make a convention. Let's say top to bottom. I mean, I think this is pretty symmetric, so it wouldn't really matter. But yeah, but usually I read it from top to bottom. So we say examples of braided tensor categories. There is one general construction called the center, or the Drinfeld center, that allows to construct a braided tensor category starting from a braided fusion category, starting from an ordinary fusion category. So let A be a fusion category, not necessarily braided. Then its center, denoted ZA, consists of the following objects. So every object is a pair called, say, Z, A gamma, where Z is an object of A, and gamma, let me draw like this, gamma X. So this is going to be a natural family of isomorphisms. So what this gamma X does, it permutes the Z with all objects in the category. So it's a collection of isomorphisms like this. So remember, A is just a fusion category. There is no braiding yet. Okay. So now we consider all objects Z for which you can permute the Z with objects in a category in a consistent way. Okay. So this gamma would satisfy our natural condition, like when we permute Z with the product of X and Y. This should be the same as permuting Z with Y first, gamma Y, and then permuting it with X. Again, I suppress the associativity constraints to keep this diagram reasonable. So if I include them, there would be 6 errors because each time you have to apply associativity first. Okay, so again, so objects in the center are objects of A along with this consistent family of permutations. Again, the name center should be self-explanatory, right? You know, this certainly look similar to the notion of the center of an algebra already. Yes. Now, the important thing is that what we get is actually a braided category because here we have, let's say, we have the object Z gamma and say Z prime gamma prime. We have isomorphism from between Z prime and Z prime Z, and it would be given by what? It would be given by we can use the central structure of Z prime and apply it to Z. So this central structure permutes Z prime with this object. This allows you to braid objects. So ZA, the center of A, is a braided, which is to be expected, right? The center of a ring is commutative. The center of a fusion category should be commutative in the categorical sense of the word. Now, a couple of comments.
One question, sorry.
Yes.
Is there any restrictions on the morphisms in the category in the center?
Yes, so morphisms have to be, you're right. So morphisms have to be defined appropriately. So a morphism from, okay, so I usually, usually people drop the second thing and they just use first for that. Yeah, morphisms should commute with the structure. So you should have this diagram. So X tensor Z prime, so it's identity tensor F, and this is gamma X, this is gamma prime X, sorry, Z tensor X, Z prime tensor X, and its identity F. So that's what I said, morphism should commute with this permutation structure, yes. It does take an effort to prove like all the statements that I made, that that's a braided category, but this is really an exercise using diagrams. So some notes about this construction. So first of all, a given object Z of A may have several central structures. Like there can be several choices for this particular gamma, or none at all. Second, this analogy that I made between the center of a ring and the center of a fusion category should be taken carefully, because the center is always sits inside the ring. Here, the center is actually larger than the original category. So, in particular, the Frobenius-Perron dimension of the center is the square of the Frobenius-Perron dimension of A. And because of the definition, you cannot really regard this as a subcategory of A, but what you do have, you have a forgetful functor, let's call it F, from the center to the original category that would just forget about the central structure, would send this pair to Z. Okay. This functor is a surjective in the following sense. So this is, well, this name surjective sometimes is used with different meanings. So let me put in quotation mark. So what I mean is this: if for any x an object of A, X is a sub-object of Fz, whereas Z, for some Z are from the center of A. Okay, so although X may not have, it is possible that it doesn't have a central structure, it's inside an object, it's a sub-object of an object that does have central structure. Okay, so like I said, this central construction, the center construction makes sense for any fusion category, braided or not. Now, if we start with a braided category, if C is braided, then it can be embedded into its center. Then there is an embedding of C inside the center, where what we simply do, we use the braiding of C as the central structure. So here an object X, it should go to what? To a pair, where the second component is this permutation. So we will use like braiding with X as a permutation. Right? So this allows you to permute objects with everything else. Yeah. So it's an embedding of C into the center. Now, it also should be mentioned, and it will be important later on, that in fact, given a braiding on the category, you can reverse it. So the reverse on C is the following. So remember, the braiding in our notation goes from X tensor Y to Y tensor X. What we can do now, we can define new braiding. I call it C reversed. And so what I'll do, I'll take CYX, that's the way to permute Y and X in that order, and take the inverse, right? So CYX goes from Y tensor X to X tensor Y. So this would go from X tensor Y to Y tensor X. Well, that's a new braiding called the reverse of the original braiding. And it doesn't really have, it does not have to coincide with the original one, unless the category is symmetric. That's a new braiding. Now, so we have another category, so C reversed. As you know, it will be C with the reverse braiding. So they come in pairs. Braidings do. Okay, so what we can now do, we can actually do the same thing for C reversed and embed it to the center, just like we did with C. Yes.
So with this embedding you have written down, the category into its center, we know that that's not all there is in the center because of this theorem about the dimensions.
That's correct.
Is there any insight into what else is in that
yes,
center?
I was about to say, well, yes. So look, so we can do the same thing with the reverse category, also embedded to the center. And these two embeddings would combine into the functor from C tensor C reverse. So there is a obvious notion of a tensor product of tensor categories. Okay, so that's that. So this combines into this functor. And that's a braided tensor functor. So it preserves tensor structure and it also compatible with the braiding of the categories. Okay. So now, well, two of them actually sit inside the center. However, this is in general, it's not an equivalence. Okay. There is still, because they can overlap. Okay, the two categories. There is still something else that sits inside the center, and it's kind of tricky question to determine the remaining object. So let me give you an example of how what center looks like in concrete situations. So let's take the category of G-graded vector spaces that we had seen last time and take its center. Then, well, you can think of vec G itself as the category of G-graded vector bundles. So this will be the category of G equivariant vector bundles on G. So let me translate what it means. It will consist of G-graded vector spaces. After all, this is what objects of vec G are. And the central structure would amount to collection of isomorphisms from Vx to Vg xg inverse. I'll call it like gamma xg, like this. Will be which would amount to the central structure on this category. These are to satisfy conditions which are similar to this, that if you conjugate twice, it's the same as you conjugate by the product. Okay, so it's a nice geometric way to think about this. Now, if you are familiar with the notion of the Drinfeld double, that's for groups, let's say. That's what it is. So the center of vec G is the same as the representation category you see, I'm excited about this, of the Drinfeld double of G. If remember, this category of G-graded vector spaces has its twisted counterpart where we introduced a Trika cycle. I think I denoted it alpha yesterday. Well, there is a notion of a twisted Drinfeld double, the alpha. It's an interesting braided tensor category, which is of course more complicated than the group G itself, but that's the simplest example of the center of a fusion category. Actually, I'm wrong. It's not the simplest. Here is the simplest. Here. Okay. Now, the first example that we defined last time was the braided fusion category associated to the quadratic form. Let us start now with the category A to be vector spaces graded by a abelian group, and this would correspond to this CA1. So I consider the trivial braiding on this category, just the symmetric braiding. Okay, so this would be the quadratic form would be 1. In this case, the center of vec A is a pointed category whose group of simple objects is A plus A hat, and this group has a canonical quadratic form H, which simply takes a pair of an element of this group, which consists of an element of A and the functional, and evaluates one on another. It's called the hyperbolic quadratic form, and that's the center of it. Now, this, in fact, the special case of that, right? Just take G to be abelian here, but this puts things in the proper kind of perspective.
Sorry.
Yeah.
I've forgotten. What does it mean, this notation with CA1?
Okay, so let me recall, because I will need this before. So what we did last time, we did the following. So given a quadratic form Q on A with the values in the multiplicative field, which means what, by the way? It means that Q of xy divided by qx, qy is bilinear form, symmetric bilinear form, and qx is qx inverse, the usual definition of a quadratic form. So given such a quadratic form, there is a braided fusion category. There is a pointed braided fusion category. I denote it like the CAQ. With A being the group of invertible objects, and Q being such that the braiding of object X with itself is the value of this quadratic form. Okay, so it is not entirely obvious, but this is actually enough to recover the whole structure of a braided fusion category up to equivalence. Okay. So strictly speaking, it's not a particular category, it's a representative of equivalence class. All right, so and when I write CA1, well, of course we can 1 as a quadratic form, the constant function, right? So you very boring one, it would give you symmetric category. All right. Okay, so let's move on. So now this analogy with the quadratic forms will be very important for today. So next thing I'll talk about centralizers, which is, I like to think of it as a categorical orthogonality. Okay, so what is that? So let us start with the braided fusion category, and we say that a pair of objects in this category C centralize each other if the squared braiding between them. You see, you can perform braiding once, you can perform it twice. And it would this composition would map X tensor Y to itself. So if this squared braiding is identity, it's a property of a pair of objects. Okay. So well, let us look back at this example. So here in CAQ, the squared braiding is given by this bilinear form. So two objects are X and Y in A. Again, so here I can use like letter X to denote the one-dimensional A-graded vector space, which is concentrated in the component X, right? So that's, I can write it like this if this is less confusing, right? Make sense? So simple objects correspond to elements of the group. So two objects X and Y centralize each other if well, if the value of this form is 1, and this is thought, of course, as an inner product, that is to say, X and Y are orthogonal with respect to this inner product. Okay, so that's where the name categorical orthogonality comes from. Okay, so but for us the condition is this. So we'll make an observation that if X centralizes a pair of objects like Y and Z, then X centralizes their product. Again, that's the consequence of the hexagon identity. You know, the braiding with Y tensor Z splits into a product of braidings of Y and Z. So and all sub-objects. But this, of course, it centralizes direct sums as well. So, which means that if B inside C is a subcategory, then its centralizer, which by definition going to be this, the collection of all objects in C that centralize every object in B. So C YX, CXY is identity Y in B. Again, the way to think of this is of an orthogonal complement, right? That's precisely what it is. So if B is a subgroup of A, then B prime is, well, subgroup would be correspond to a subcategory of this, right? Of vector spaces supported on this subgroup, and the centralizer is just the orthogonal complement of that. So this thing is a fusion subcategory. It's a fusion subcategory of sort of an orthogonal complement. Okay, so this brings us this whole geometric flavor into this theory. You can talk about orthogonality, you can talk about Lagrangian subcategories, subalgebras, etc. We'll talk about all this. But for now, we can look at it closely. And first of all, we observe that there is a canonical thing. So you can look at objects of C that centralize everything in C. So it's a C prime, denoted like this, Z symmetric. So this, I write it like this, symmetric center. Now, this is very different from the center that I defined minutes ago. So this is a different center, okay? So this center is large. It's a braided category and very non-degenerate one. So this is indeed a subcategory of C, okay? So symmetric center, or it's called the Müger center sometimes. Müger center. For Michael Müger, who introduced this thing. So this would be what? This would be all objects in C that centralize everything else in C, right? For all Y in C. Again, in the example with the quadratic form, this would be the radical of the quadratic form, the radical of this bilinear response to the radical. All right, now the next depends on how big this radical is. It can be, first of all, observe that the unit object certainly belongs to the symmetric center. The unit, the braiding of the unit object is given by the composition of unit constraints. So Cx1 is what? So it's x tensor 1 to 1 tensor x. This is x, and this is left, and this is right inverse. Okay. The square of this is identity.
This C prime,
yeah,
is obtained with the definition above, where B is equal to.
That's right. So you just take this B and set it to be the whole category.
Okay, then I was confused. Then X lies in the center of C.
Which one? Which this X?
Yeah.
Okay, so this is the collection of all x's that centralize every Y in C. It lives in C.
Yeah. No, I'm confused because in the previous line it belongs to the bigger category.
In which line? In this
B
one?
prime, yeah.
So here x is in C and here x is in C, right?
Yeah, but then we are looking at C contained in Z of C.
I'm sorry, which to which line do you
So
refer?
now in the second line, we are taking B equal C and C equals Z of C.
That's symmetric of C.
Yes, C equals C and B equals C.
Ah, okay. Okay.
So we just said, okay, so this is a general definition of the centralizer, okay? So now we said, as a special case, B to B equals C, right?
And C equals.
And C equals.
Okay, I thought C.
No. That is now, this was just an example, and yes. So, okay. So there is always this. So the symmetric center can be as small as the category of vector spaces and as large as the whole category. So this motivates the following two definitions. So if the symmetric center is trivial, just the smallest possible category, just multiples of the identity object, right? Then what it means? It means then what we have is that the squared braiding is identity. Sorry, that's not what I wanted to say. Then we say that C is non-degenerate. So these are the most interesting braided categories. So for example, CIQ is non-degenerate. This is the category I just recall. If and only if the quadratic form Q is non-degenerate, in the usual sense of linear algebra. Second is that center, the Drinfeld center that we constructed, is always non-degenerate. Fusion A, its Drinfeld center ZA is non-degenerate. We had seen example of this, when for a pointed category, it was the hyperbolic quadratic form, which is non-degenerate. So it's consistent with that. Now, we will see that in general, the study of braided categories is reduced in some sense to the study of non-degenerate ones. Just like the study of quadratic forms, you can mod out by the radical, right? And what remains is a non-degenerate form. So same strategy works here, right? Next, so here is another extreme. So if the symmetric center of C, and please don't be confused by this notation. I always write Z symmetric for the symmetric center and Z for the Drinfeld center. So there should not be a confusion. So if the symmetric center is the whole category C, then the squared braiding is identity for every pair of objects. And such category is called symmetric. That C is symmetric. Okay, now it's very hard problem to, and of course not solved, and probably will never be solved, to classify all non-degenerate categories. It is possible to classify all symmetric braided fusion categories. This was done by Pierre Deligne. And let me recall his result. So let me mention two examples first. So examples of symmetric categories. So first example would be this. Take a finite group G, the category of representations of G, with its usual symmetric braiding. So what does it do? Same as for vector spaces. You pick a simple tensor, VW, and reverse the order of factors. Certainly symmetric braiding. Such categories are called Tanakian. There is a way to twist this thing a little bit, as follows. Now, suppose we have the same thing, a group G. And now let Z inside G be a central involution, an element in the center of the group. Now, this is really this is the center in the sense of group theory. The center of a group has nothing to do with the previous things that I introduced, such that Z squared is 1. So order it must. So now I'm going to define a new symmetric category, GZ, G comma Z, as follows. So this is going to be the same as rep G as a fusion category, but I'm going to introduce a new braiding. So here is what I will do. I'll take VW to be irreducible representations of G. And I define CVW, the braiding morphism. It's going to be this. So there will be two cases. It's going to be negative of the transposition VW if Z acts on V and on W by -1. So now this is a central element, right? So by Schur's lemma, it acts by a scalar on every irreducible representation. Yes. And because the order is at most 2, the scalar is either 1 or -1. Yes. So if it happens that it acts by -1 of V and W, then we put minus sign. Otherwise, we don't do anything, we just reverse. If otherwise. So this innocent modification of the braiding depending on this central element. Okay, such category is called super-Tanakian. So the simplest example of a super-Tanakian category is the category of supervector space. Supervector complex vector spaces, which is of course symmetric, and in this notation it would correspond to the group Z mod 2 with a non-trivial element Z in that group. Okay, so it's an example of super-Tanakian. Okay, and the theorem of Deligne tells you that this is all. Any symmetric fusion category is either Tanakian or super-Tanakian. Any symmetric fusion category is either Tannakian or a super Tannakian. So you can combine this notion at once if you, what did I say here? Well, I say it's of order at most 2, but clear that if order is 1, then you just get the Tannakian category, right? So this is kind of the most general form of such a category. All right, now, well, this is a great news because you see, well, we like to think that we understand finite groups better than we do tensor categories, which is, I don't know, I mean, it's a tricky statement. Of course, you know, finite groups can be very complicated, but at least we know what to do with them. Okay, so and the general spirit will be tried to mod out by the group theoretical part of a fusion category and study what remains. All right, this is what I'm going to do in subsequent lectures. So for now, let's discuss some properties of non-degenerate categories. Properties of non-degenerate categories. Before I proceed, any questions? Okay.
So these categories, they are classified up to braided monoidal equivalence.
Up to braided monoidal equivalence.
And is there a way to make it more explicit, like
it's
more explicit in terms of is there more data group theoretically which describes them without like saying we classify them up to braided monoidal equivalence?
I'm not sure what you mean.
Like in each equivalence class, we have probably monoidal equivalence between 2 such categories.
Well, this pair G comma Z is a complete invariant. You know, like the is a complete invariant, meaning that if 2 such categories are equivalent, then there is an isomorphism, you know, from G to G prime that takes Z to Z prime. Make sense? Yeah.
Yeah. Thank you.
So, okay. So some properties. So let's relate them with the concepts that we discussed earlier today. So now, so suppose C is non-degenerate. Then you have this double centralizer theorem. So if B is a subcategory of C, then it's a second centralizer coincides with B. Simply how the second orthogonal complement of the orthogonal complement is the original thing, provided that your inner product is non-degenerate. So in general, of course, it would be a subcategory of the second centralizer. Second, the dimensions of centralizers behave the same way dimensions of orthogonal complements do, namely the Frobenius-Perron dimension of B times the Frobenius-Perron dimension of the centralizer is the Frobenius-Perron dimension of the category C, which also makes perfect sense because the bigger the category, the smaller the centralizer. I mean, so here things are multiplicative, right? So yes, so I understand, like in the vector space, I mean, let's say if you have vector space of the finite field, then the dimension of our category will not be the dimension of that space, but the number of elements in that vector space. Okay. All right. So the third is this. Like we have seen this before.
I have a quick question.
Please.
Is for the number 2, is that are we assuming that C is not a general?
That's right. Yes.
Okay.
That's for non-degenerate. Otherwise, there is a similar formula, but the dimension of the symmetric center will show up. I think you have to multiply here by the dimension of the symmetric center.
Right. Thank you.
Yeah, sure. Okay. So now this was the.
Question. Is it possible to reconstruct C with B and B prime?
No, because for instance, you know, so for example, like start with a symmetric category rep G, okay, and that's embedded into the center of rep G, and it is symmetric, so it coincides with its own centralizer. So you cannot really, you know, reconstruct this thing like from its subcategory. The problem is that B and B prime can overlap.
I mean C, not the center.
That's right, but this is kind of an example. Like take this C and take this to BB. What you can do, okay, maybe I should mention this is the next property. So if C is non-degenerate and B inside C, a subcategory, which is also non-degenerate, then you have this factorization. You can factor C as a tensor product of B and B prime. Again, there is a linear algebra counterpart. If you have a non-degenerate, this metric space, and inside this metric space you have a non-degenerate subspace, this complement is also non-degenerate and splits into direct product as braided tensor categories. Yeah, the only way to compare a braided tensor categories is by means of a braided functors between them. Okay, so one last thing that I wanted to mention is like this. So we have seen, maybe I should use another board for that. So there is a criterion of another criterion for non-degeneracy in terms of this braided tensor functor that we have seen before. So for any braided category C, we saw a braided tensor functor from C tensor C reversed to the center. Let's give it a name. Let's call it F. And well, there is a theorem that says that you see this exists for any C, non-degenerate or not. Okay, the theorem says that C is non-degenerate if this F is an equivalence, is a braided equivalence. So, in other words, if your category with you begin is non-degenerate, then the center is rather, well, it's rather boring in the sense that it reduces to C. It has C and C reversed inside and nothing else.
This is just like if, not an if and only if.
Yes. So if that's right, I didn't say this, like if and only if. So this is related to this previous factorization result, right? So C sits inside its center, and its complement is also non-degenerate. All right. Now I'm not sure my watch is correct. All right. Yes. Now sometimes you would see the name modular tensor category, and I don't plan to talk a lot about them, but this is a close relative of non-degenerate category. So to introduce it, I need some additional notions. So a spherical structure on a fusion category is a tensor isomorphism, is a natural tensor isomorphism between the identity functor and the second double dual. So what I mean by tensor here is that f of x tensor y should be fx tensor fy. I'd like to note that in any fusion category, object and its double dual are isomorphic. However, what we are asking here is much more. We ask for a consistent way of identifying them that respect the tensor product. Okay, and believe it or not, it's an open problem whether such a structure always exists. So open problem. V is an object in C. So this is what I'm trying to say here, that I need a notation for this spherical structure. It's the collection of isomorphisms from V to V double star that commute with morphisms in the category, right? And respect tensor product. So, I'm sorry, say again?
You're missing an isomorphism to make it tensor.
Like here, right? It's here? Oh.
I think you're missing the tensor here. Because you don't know that X double dual tensor Y double dual is equal. So
Well, we do. I mean, I don't think I mentioned that, but it's certainly that if you take, so when you take the dual of the product, so if you do it twice, you get X star.
but I mean, it's not equal. There's an isomorphism.
They are isomorphic. Right?
Right, yeah, so you're missing the isomorphism there, inequality.
Okay, well, okay, yeah, so this is modulo of this isomorphism.
Right.
Yeah, okay. You can draw like, commutative square.
Right.
Okay, yeah, so let me mention the open problem, okay, the exciting part. So the open problem is that it's not known if does a fusion category have a spherical structure. So it's known to be true in all known cases, and then for some classes of fusion categories, it's possible to prove that indeed the spherical structure does exist. For instance, it's true for categories that come from representations of quasi-Hopf algebras and some others, but not in general. So, and the modular category, now it's a deep subject and would require kind of several additional lectures, but I can mention at least what that is. So a modular category is a non-degenerate braided fusion category with a spherical structure. So spherical structure, although I just mentioned it in passing, but it's responsible for many good things. Okay, it would allow you to take traces in this category. Yes, please.
Maybe I'm missing something, but I thought that just having a tensor isomorphism and the category is pivotal.
Yeah, that's right. Yeah, yes, that's true. Yes, so spherical structure. Okay, then I have to say a few more words, but I think it's for good. Yes. So one would need a spherical structure. So spherical structure would allow you to take traces of the category. Namely, so let's fix such a spherical structure. Fx is an isomorphism from X to X double dual. Then you can introduce this composition. So you can start with identity, take evaluation. And now, in general, we cannot compose evaluation with co-evaluation because they have different domain and codomain. What we can do, though, we can apply the spherical structure to the first component and have here like this. And then apply evaluation, get one. So the result is a scalar that depends on f, right? So and one, it's a complex number. In fact, it's possible to show that it's not hard to show at all that this number is non-zero. Okay, so we call this number the dimension of x related to f. Now that differs in principle for the from the Frobenius-Perron dimension that we introduced previous. Look, they even take values in different fields. The Frobenius-Perron dimension is a real number. This may very well be a complex number. Okay, so this is the dimension related to f. So it does depend on f, on the choice of the spherical structure f. So it depends on the choice of such an isomorphism f. So we say that in a spherical category is spherical. In spherical category, we require an addition that the dimension of x and dimension of the dual are equal. Okay. So if this is so, then in fact, in this case, dimension of f is a real number, but that's not obvious from the definition. Okay, so if this is satisfied, then it's non-zero real number. So
I have a quick question.
Yes, please.
So when I'd seen the definition of spherical before, it was something that seemed stronger, which is like you have the left and right pivotal traces being the same, which like clearly would imply this, but it's not completely obvious to me that the other implication is true.
Well, yes. So the left and right pivotal traces, they related to each other by replacing x by x dual and taking inverse. So that's really the same. So for now, this notions can be given in any tensor category, not semi-simple one. So here I am taking advantage of this being semi-simple and requiring this condition. Okay. Okay. So all this was needed to introduced this notion of a modular category. So it's non-degenerate braided fusion category with a spherical structure. So for I'm not going to
Just a clarification, I got a bit confused. So these things in the new board are like addition to the definition of
yes, so this
spherical
is a
structure.
continuation of definition. You should read it like this, like draw like a diagonal.
Okay,
Like,
thank you very much.
All right. So yes. So, but you know, it's an interesting subject on its own, the theory of modular categories, and there is a representation of a modular group associated to it. But for my purposes, I'm not going to use the spherical structure much. Okay, it's non-degeneracy that is going to be important. Okay, so I just mentioned this in passing because you see this thing very often, and you know, people kind of tend to confuse the notion of non-degenerate and modular. All right. So this. So this will be like all for today.
As usual, we've had lots of questions. Does anybody want to ask any more?
I think I missed this in the middle, but you briefly mentioned, or someone else mentioned pivotal. Could you just quickly say again what
So
the difference was between
pivotal would be
and
just this part,
just the first?
just existence of a tensor isomorphism.
Okay.
And it's yes.
And then if you add the constraints and the dimensions, then
Yeah.
it becomes spherical. Okay.
Any last questions?
Yeah.
Oh,
Because you mentioned,
just pass the microphone if you would.
so you mentioned that open problem is known in some cases. I didn't notice what you said. Can you?
Well, it is known, for instance, if the Frobenius-Perron dimension of your category is an integer. That would include in itself all Hopf algebras and quasi-Hopf algebras and other things like Ising category, for instance. So I mean, it's true for everything that we know at present. So.
All right, no questions in chat. Well, one at the back.
Yes, you mentioned that the Frobenius-Perron dimension is quite different in principle to this dimension. Are they ever equal, or is there any relationship?
No, in general, no, because there can be different choices of the spherical structure.
Sure.
So which would differ. So what is true, and that's what I was saying, that in some cases, you can choose a canonical spherical structure that gives you the Frobenius-Perron dimension. So for instance, like if your category is a representation category of a Hopf algebra, that's the case. Okay. But in general, that's
all right. If there are no further questions, let's thank Dmitri one more time.